the next test. So it's come to my attention, although this isn't why, but that there is also another test that week. I am actually going to go ahead and move my test to the 4th. So the other, that's good for a couple of reasons. It's also nice because I think you guys have an outstanding homework right now. I'm still grading a homework that I'm going to get back to you on Friday, but then I'm going to receive one here, and I want to be able to give it back to you, or I'm going to receive one, on the 31st. And I want to be able to give it back to you on the 2nd and have a turnaround on that and have that material be on the test, because it was already kind of a long time ago, and I don't want you studying things from too long ago the first time I tested. So we will have a more in-depth conversation about the sort of the boundaries, content boundaries on that test on Friday. Okay. So let's go ahead then, and without any further ado. So from last time, we were talking about sort of some nice, mathematical results that come from the case where you have a spherically symmetric potential, which will always be conservative from the derivation. So in that case, we started talking about two particles. Okay, so let's just remind ourselves from last time. We had these two particles, particle 1, particle 2, origin here, R1, R2. And this was the vector R1 minus R2. Okay. And in that case, we found that we could write a potential energy for this system. And, well, I guess I should be very clear. We were considering this for the case that we just had maybe like a gravitational force. Or do we want to do actually looked more like a Coulombic repulsion. That doesn't really matter. So this was called the force on 2 by 1, and this is called the force on 1 by 2. So that first subscript is the thing that the force is acting on. Okay, and then we did an example where we had a force on 1 by 2, and sure, if we want to think about the gravitational, we would have G M1 M2 over R1 minus R2's magnitude cubed times the vector R1 minus R2. So yes, that magnitude of the force is always going to be Gm1, M2 over the distance between their centers squared. But in order to avoid having to write this as a unit vector, I went ahead and wrote that as cubed. So for those of you who didn't have me in introductory physics, this is how I did it in introductory physics as well. Those of you who haven't seen that before, that's why we're doing this, so that we don't have to deal with the creation of a unit vector, which would just be an extraneous step. Anyway, so what we found here was that we have a force that depends only on the difference with R1, R2, as it must because of translational symmetry, but also is a force whose magnitude does not depend on theta or phi. As a result, that's called spherically symmetric, and it will also, its magnitude, because its magnitude doesn't depend on theta or phi, it will be a conservative force. And so for this system, from last time, I'm not sure how much I want to review from last time. I can write an expression for potential energy of the system. And I can go ahead and call that U12. So that the total energy of the system would be kinetic energy of object 1 plus kinetic energy of object 2 plus this potential energy term. And the thing about this potential energy term is that, you know, that potential energy, 1, 2, is going to be some function of R1 minus R2. And if I ever want to know the force on object 1 by object 2, it'll be minus del sub 1, U12, where del sub 1 was defined as x hat times the partial with respect to x1 plus y hat times the partial with respect to y1 plus z hat times the partial with respect to z1, those being the potential locations for object 1. And similarly, then we also found that F2, which must be equal and opposite to this, turns out that we can write that as, because it would be positive del 1 acting on U12, I can, instead of taking a derivative with respect to del 1, I can take a derivative with respect to del 2, and that'll give me that minus sign that I need to make that positive. So I can also note that this is equal to minus del 2 of U12. Off the page. Okay. So these are just some of the highlights from last time, in that we made sort of some new math. Did some nice stuff. We obviously found and derived from last time that the total energy of this particular system is going to be conserved because it is, you know, an isolated system, and the only force acting is the interaction force between these two, which is spherically symmetric and therefore conservative. So my last result from last time was that dt plus u is equal to 0. Okay. So meaning that the energy will be equal to a constant. Okay. So I'm going to go ahead and pick up from there. So let's start talking now about elastic collisions. And just to be clear, I don't normally review that much from last time, but since there was no video, that's kind of why I gave that a few minutes. All right. So what we are going to do now is we're going to think about elastic collisions, which will be collisions between two particles that interact via a conservative force. All right. So similar situation to this. And this force will also be like that in that the magnitude of the force will go to 0 when the distance between the two particles goes to infinity. And what that allows for is that the potential energy when the distance between the two particles goes to infinity will go to a constant. And whenever you have sort of an arbitrary constant in your potential energy, you're free to call that 0 if you would like to. It's just sort of a choice of what you're calling R sub naught when you do that. All right, so just to, I know I said a bunch of stuff, so I'm going to write down a few notes about it. So right now we're going to start thinking about collisions between two objects that are going to interact via a conservative force. All right. And this force has the characteristic, so for which the magnitude of the force, let's just say, goes to 0 when the distance between the two objects, which I'll call R, goes to infinity. If that's the case, then the limit as R goes to infinity for the potential energy associated with that force will be a constant. And we will go ahead and let that constant be 0. So that means that we're choosing our R naught to be at infinite separation between the two objects. Okay. So when we think about these collisions, again, it's going to become an even more loaded word now than it was before. When we think about these collisions, we're going to start with the two particles far apart. And this word far means that it can be well approximated as infinitely far separated. So that implies that the potential energy initially could be treated as 0. And that the kinetic energy initially will just be T1 initial plus T2 initial. Okay. And then what they're going to do is they're going to approach each other, they're going to collide, and then they're going to recede from each other again until they are far apart. So what do I mean by far apart again? I mean, again, where the potential energy can be approximated as 0 because they are far apart. And your author does this cute thing where he uses FIN for final. So I'm going to do the same thing. All right. So what that means is that since we have, first of all, let me go ahead and write the same thing I did before. So in the end, the final kinetic energy of my system is equal to T1 final plus T2 final. Okay. So because these two objects, they don't have any external force on them that we're going to consider, and therefore we have no non-conservative external forces on them. They interact by conservative force, so therefore we have that mechanical energy will be conserved, just here. All right, so what that means is that since energy is conserved for this system, that means that T initial for the total system is equal to T final for the total system. Because clearly E is equal to T plus U. And the initial and final potential energies are both 0. Okay? All right. So this is a result that we see for a lot of different physical systems. We see this for billiard balls because they are solid and they have sort of they don't have a theta dependence in terms of the repulsive force between them. Now, if they weren't perfectly round, we wouldn't have that. But anyway, so they're a good example of having a spherical symmetry. They also continue to have that spherical symmetry after the collision. They don't deform. So they do deform during the collision, but after the collision, they go back to being spheres again. So what that means is that they are solid, and when they are deformed, they kind of act like a spring. They can store all that energy, and it can come back. Now, pieces of putty will not do this because when they deform, there is no potential energy associated with it. Bags of sand, same sort of thing. All right. There's no restoring force in those cases. But these objects are literally solid, and therefore their atoms sit on a lattice, and when it's deformed, the lattice will have a strain stored in it it will stress itself back to its original position. All right? Okay. So, couple of things to keep in mind here. I guess I should note that this is only true for the conservative forces, so it doesn't hold for pieces of putty and things like that. for which there are no potential energies associated with certain forces, and therefore they're not conservative. Also, it won't hold if we have more than two particles. Throughout. So that means if the two objects come in and they collide and one of them breaks into two pieces, we won't have this anymore. Right? Because that came from a derivation that we did for just two particles interacting through a conservative force. All right, so I think that's what we got. So let's go ahead and move on now to energy of multiparticle systems. All right, so we're going to begin this again. I'm going to stick with so far so good with your author, in my opinion. Hasn't lost me yet anyway. So I'm going to, and I kind of like this particular derivation as well. So we're going to start by talking about the special case of four particles. Would it be better if the lights were off, or are we okay with the lights on? Just kind of noticed something was different. You want them off? Go ahead and turn them on. Thank you, Darcy. Okay, so we've got the special case of four particles. Let's go ahead and draw them. 1, 2, 3, and 4. All right. And so, for instance, if I wanted to notice that these two are interacting, there's going to be some force like so. Let's remember that by our convention, this one would be called F3-4 because it's on 3 by 4. This force here would be called F4-3 because it's on 4 and by 3. Okay. So in this case, I've got a total kinetic energy of T1 plus T2 plus T3 plus T4. No problem there. And also, I'm going to allow there to now be an external force on my system, but I'm going to have that external force be conservative so that I can have a potential energy associated with it. So I'm going to say also, for this particular case, there is an external conservative force. So that I will have the external force on each object. So let's think about objects of alpha, where alpha can be 1, 2, 3, or 4. And that will be equal to minus del alpha, like I just introduced the del operator a few minutes ago, acting on the potential energy of object alpha associated with the external force. And that will obviously be a function of r sub alpha, location of that object. All right? Okay. So in this case, we can also have internal forces, though. Like, for instance, this force here or this force here, if I wanted to write the force on object 3 by object 4, well, then if I go ahead and I'm going to go ahead and stipulate that all these are interacting through, again, let's make them spherically symmetric forces, and therefore they'll be conservative forces. Then what I can do is I can note that this will be equal to minus del with respect to the components of R3 on the potential energy that is associated with the two particles, 3 and 4. And to be clear, I'm going to start sort of following a rule with my subscripts here, that the first subscript is lower than the second subscript, so that I'm not doing a double counting in my potential energy, and we'll talk about that more in a bit. But clearly there's only one potential energy associated with these two particles, 3 and 4. And I'm going to go ahead and call it U34. I'm going to put its lower value first. Okay. All right. So that similarly, I would write that the force on object 4 by object 3 would be minus del 4 acting on U34. Noting that U34 is a function of R3 and R4. All right? Okay. So what this does now is, like, I've already got an expression for my total kinetic energy of my system. I want to write an expression for the total potential energy of my system. And let's do it. I'm going to have a potential energy associated with the external conservative force and one with all these internal conservative forces. All right. So let's go ahead and note. All right, so I'm going to have U1 external plus U2 external plus U3 external plus U4 external. And then I need to add up all these internal forces. Now, I don't have a potential energy between a particle and itself. All right, so there will be no U11. There will be a U12. There'll be a potential energy associated with those two particles and their locations relative to each other. There won't be a U22 though. And there will be a let me come up here to particle 3, a U13 and a U23. Noting that this object here, so you guys probably saw this argument from 240 to 250, but I'm going to refresh your memory. You can sort of think of getting the potential energy in here. Let's think of all these objects as maybe being positively charged particles. Let's say I take object 1 and I take it from out here, way out here at infinity, but there's no, let's imagine out there's no external field, just for this one moment. And I move it there, which takes no work because I didn't have to apply any force to get it to move. And then I take object 2 from infinity and bring it in here. So now I've had to do some work associated with that by bringing these two charges closer together. All right? And so that's the term that is here. All right, so now I have to imagine bringing in particle 3. In order to do that, I have to do a work against force from object 1 and the work against the force from object 2, which gives me the potential energy associated with charges 1 and 3 plus the potential energy associated with 2 and 3. And last but not least, I have to bring in 4 from infinity, and that's going to give me plus a potential energy associated with object 1, a potential energy associated with object 2, and a potential energy associated with getting close to object 3. All right? And so that's my expression for the total potential energy of my system. Now, if I wanted to know, for instance, the net force on one of my particles, I could get that from this expression for U. All right? So, I'm not sure, I guess I can show you that. So, if I wanted to know the net force on particle 1, I could just take minus del with respect to x1, y1, and z1 and act on U. All right? Now, this one's going to depend on R1, and these 3 that involve 1 are going to depend on R1, but the rest of them don't actually depend on R1. So the expression that I will get out of here will ultimately be, let's go ahead and say F1 external, because it will act on this guy. It won't act on either of those. And then I'll get F12, because it will act there, plus F13 when it acts on this term, and plus F14 when it acts on this term. All right? So when you have an overall expression for potential energy that depends on the locations of 1, 2, 3, and 4, it's kind of a powerful thing to have. All right. What else do I want to say about this? In this case, we should note that I have these conservative forces acting internally. I have a conservative external force. There are no non-conservative forces. So that once again, I do have that the energy is conserved. And I'll say with this definition of the potential energy, So we're going to have energy conserved for this system. There's also a nice derivation of that in your book, but I don't think it really does much for us to do it. So I don't think that we need to do that. All right. So that's pretty much what I wanted you guys to think about, is that we have an isolated system. All external forces, if they exist at all, are conservative. Internal forces are conservative. Energy, we can write a nice expression here for a potential energy of the entire system. And we can do some nice things with it. Obviously, we have energy conservation, and we can also find forces on the interacting particles for that. Okay. So now that we've done the case of 4 particles, let's write something a little bit more general for the case of n particles. All right. So in this case, first thing that I wrote up there was an expression for kinetic energy. I'm going to do that again. T is the sum of alpha equals 1 to n T sub alpha. All right? Similarly, I have this expression for potential energy that I would like to write for the n particle case. So again, I'm going to have external plus internal, assuming that there is an external conservative force acting on my system potentially. And so what I'm going to have is, for my external force, sum for alpha u sub alpha external. And for my internal force, I'm going to have the sum over alpha and the sum over beta, which must be greater than alpha, of u sub alpha beta. And I didn't specifically use the word internal on those, so I'm going to stick with that the way that it's written. Okay. And the thing to notice here is that beta must start at 2, for instance, because it's got to be greater than alpha, and alpha starts at 1. All right. And so again, what I've done here is, just to be clear, I did this so that I wouldn't have double counting. I did this so that the potential energy associated with particles 1 and 2, being at their respective locations, would be included as U1, 2, but it would not be included twice, because I don't want U2, 1 to show up, all right? Because there's just one potential energy associated with those 2 particles. All right. All right. And this result here, for any particle, I can find the net force on that particle by minus del sub alpha acting on U. And similarly, up here, for this case, I will still have that the total mechanical energy system, which is total kinetic energy plus total potential energy, will be a constant, because so far I'm still describing a situation where I have only a conservative external force, and the internal forces are spherically symmetric and therefore conservative. All right. Now, if it ever were to happen that I did have maybe this external force was non-conservative, or maybe some of these internal forces were not so spherically symmetric, then I would have to take into account that the energy can change. Let me go ahead and start from the beginning. E final equals E initial. In which case I'd have to remember my work energy theorem, and for an incremental time period, dE will be equal to the increment of work done by non-conservative forces during that time. Okay. Just to cover all of our bases. But this is just sort of an otherwise. I really want you guys to know, for the case that we have the external conservative field and internal forces being spherically symmetric. All right. So another generalization that I can take to n particles would be, what if there are n particles that are sitting on a lattice, also known as a solid extended object. So let's talk about that. All right. So in the case of the solid object, I have an internal potential energy, which is, let's just use our expression from above, U sub alpha beta. Okay. And when I use this word solid, again, physics code word for something ideal, that's often a good approximation when it's a good approximation. So what I mean by solid is I mean that the neighboring atoms stay in their same arrangement relative to each other, and as a result, these potential energies of each, due to the presence of their neighbors, will also remain the same for something that is purely solid, that we can treat it as ideally solid. Okay? So in that case, then we have that this will be equal to a constant. So that's equal to a constant really for a couple of reasons. Because it's associated, well, first of all, it's going to be associated with the central force because that's how atoms and molecules interact, is through the electrostatic force. But also because of this word solid, meaning that they don't get rearranged or moved relative to each other. Okay. So I've got my internal potential energy will be constant. That's pretty much the most important thing. So we're going to consider an example here where I have sort of a cylinder that's allowed to roll from an initial position to a final position down a hill. And let's note that the height of the hill, we can call it h. That'll also be equal to the distance between the center of the object when it's at its lowest point and the center of the object when it's at its highest point. Those will both be h. Okay. So initially, the system's going to start from rest. So initially, I'm going to have a potential energy, and it'll just be associated with an external field. Specifically, in this case, it'll be, let's say that the object has a total mass of m times g times y initial. All right. And in the end, let's go ahead and call this location here as our location R0, where u is 0. And so in the end, I won't have any potential energy to worry about, but I will have kinetic energy. And I will have potential kinetic energy of a couple of types. Again, I'm just trying to remind you that when we have an extended object that is rolling, we have two types of kinetic energy associated with that object. We have the fact that its center of mass is moving from here to there, translating. So I've got 1/2 m times the velocity of the center of mass, final, squared. And then I also have kinetic energy associated with the fact that the object isn't just moving from here to there, it is also spinning as it moves from here to there. So we need to put a kinetic energy associated with that, for which we will use 1/2 times the rotational inertia times the angular velocities final squared. All right. Now we are going to use the fact that this object has been said to be rolling and decode that to mean rolling without slipping. When something rolls without slipping, its center of mass moves from here to there at a rate that is equal to the radius of the object times the angular velocity of the object. Again, that's that same relationship that we used actually with that tipping example too. That distance rolled is equal to r delta theta as well. All right, so I'm going to go ahead and make my substitutions here. Plus 1/2 rotational inertia of a cylinder. It's solid, so it's 1/2 mass of the object radius of the cylinder squared. And V final will be, omega final will be V final over radius. And that's that object I need to square. So as a result, I get 1/4 mv final squared, 1/2 mv final squared plus 1/4 mv final squared, also known as 3/4 mv final squared. E final will be equal to E initial. And because I have the only external force acting is conservative, and U internal is also constant. And let's go ahead then and write that. T final plus U final equals T initial plus U initial. And initially my object was at rest. And finally, I went ahead and said my object was at a location where I can say its potential energy is 0. And I have, I'll go ahead and make my plug-in, 3/4 mv final squared is equal to mg y initial, which I can go ahead and call h. How's that? My m's cancel, and v final is 4/3 g times h, 1 square root. So that's just fun for old times, isn't it? All right. So in terms of rigid objects, when we're considering them, there's a couple of things to keep in mind. If we're considering that they're solid, their potential energy, their internal potential energy will be a constant. In the case that they are extended, we'll also have to consider that there can be a kinetic energy associated with their rotation. And that's what I want you to get out of that. All right. So, oh, thank heavens, we're done with the chapter. Chapter 4 is over. That was a really long chapter. So I want to start chapter 5, and I am going to go ahead and do it now. But I want you to know that this is also a longest chapter, but I don't want to get stuck in the weeds like I did with 4. I'm going to sort of do a little bit more sort of selecting. So please do read, because I'll be less presenting and more selecting. And I really think you guys are going to love Lagrange. I'm like so dying to get to Lagrangian mechanics, because I want you guys to remember that everything you've learned so far in mechanics, you learned from Newton's laws. But wait, there's more. All those results can come from Lagrangian mechanics, which is a totally different point of view, a different set of math, and all those results can also, but wait, there's still more, come from Hamiltonian mechanics. So I really, really want you guys to see these alternate formulations, because again, it's just fun when your minds get blown. So, but this chapter is not going to blow your mind, I don't think. Chapter 5, it's on oscillations. And again, it is a 50-page chapter that I would really ask for you to read so that we don't get too bogged down in it. So for now, we're still doing Newtonian mechanics. And we're going to continue to do that here. So the cool thing about oscillations is that they're basically everywhere. I mean, anytime you kind of have a collision, you hear that sound that comes out. That's because I deformed something from a position or arrangement of stable equilibrium, and when it was released, it overshot the equilibrium point, and it went back and forth between turning points in that potential. And as a result, the air was compressed and rarefacted, and then the sound traveled out. So this is something that happens a whole lot. So when are we going to think about this? We're going to think about this anytime we have a system that's displaced from a stable equilibrium. And that's going to happen a lot because systems usually hang out in stable equilibriums. So what we're going to think about is now and then that displacement will be small, sometimes called a perturbation. And I mean that small in terms of only the first term in the Taylor expansion contributing is what that, a lot of times that's what the word small is going to mean, right? So if the displacement is small, then the type of oscillation that I get has a special name. It's called simple harmonic oscillation. And it can be well described by linear combination of trig functions and things. These are going to be found to have constant periods associated with them. that are the basis for measurement of time. It's very interesting to think about what time would be if there was no such thing as periodicity. If nothing in this world were periodic, periodic just means that it repeats after some amount of time. Could we define time? And the answer is no, and so then you become, what is time? All right, anyway, so that's kind of a fun thing to talk about, but I'm going to just keep going. So in this chapter, what we are going to do is we're going to start talking about with this simple harmonic oscillations, but then we're going to move to the case where we have damped oscillations. We're also going to move to the case where we have driven oscillations. And then we're going to have oscillations that are driven by a periodic driving force. And that is actually going to be a little bit exciting because we're going to get to do Fourier analysis with that. All right? So that's going to be kind of cool math that we get to do for the first time there, but you will be doing it all the time for the rest of your life probably. So, all right. So let's start at the beginning, Hooke's law. All right, so I'm going to sort of imagine a physical system where I've got a mass that has been attached to a spring that is attached to a nearby wall. It's sitting on a frictionless surface. And originally it's sitting sort of at an equilibrium position. So at this position here, I could say x equals x naught, but why not just go ahead and call that location 0? And then some later time, I'm going to perturb that system. Maybe I'll just kick it, or maybe I'll displace it and release it, like so. In this case, I've displaced it to some new location over here, which is x, because I'm calling this equilibrium position now x equals 0. And when I do that, when I displace it to that location x, then I have forces I need to think about. I've got, obviously, its weight and its normal force, and in this case, I'm sitting on a horizontal surface. So, and there are no other forces on it, so normal force is just equal to weight. But I will also have this force here, a force that is sort of called, it's called a restoring force, because it's trying to get that object back to an equilibrium position, and that's just the force from the spring, which is well described by Hooke's law. I'll call it force from the spring. How's that? Force from the spring. Okay, so the force from the spring is going to be a function of x. And in my drawing, it's going to have a magnitude of kx. It's going to get greater the greater you get away from your equilibrium position. And it's going to be toward the equilibrium position. So when I'm in the positive x direction, it's in the negative. When I've displaced it in the positive x direction, the force is in the negative direction. And that minus sign takes care of it, because even if my displacement had been to the negative x, as a result, my overall force's x component would be in the positive x. So let's just be clear, this is just the x component in my drawing. Okay. So, and from this expression for the force, let's be clear. So this is really our statement of Hooke's law. And if you want that to be a vector, that's fine. You can put a hat, an x hat on it. Now, we will also have, whenever a force is of this form, where it's a function of location, obviously, we will also have a potential, and it's also path independent because it's one-dimensional. Therefore, we will obviously also have a potential energy associated with it. With that variable, and the form is 1/2 kx squared, which we learned also before. Okay, so this is, let's go ahead and name a couple things. This is Hooke's law. This guy here is our potential energy. And so you're going to see that's going to be our potential energy near any stable equilibrium point. Now remember this word, again, this word near is going to have a loaded physics meaning it's not at that point, or else x can be treated as 0, but it's near that point, so only the first term in the Taylor series expansion needs to be considered. Okay. So, how am I doing on time? Okay. So, you know what? Let's see where this expression comes from. Let's do it. So, I'm going to Taylor expand my potential energy about x equals 0. And so you can think of this as x minus x naught, except that I went ahead and let x naught be 0. So it's just u of x close to x. And that is obviously equal to u at x equals 0, plus the derivative of u with respect to x at x equals 0, which I'm going to write as u prime, times dx. Again, for my Taylor expansion, my next term will be 1/2 the second derivative of u with respect to x at x equals 0 times dx squared. Plus and so on, but the rest of the terms are negligible. And in this case, the amount by which I have changed x can also be called x, because it's just dx would just be x minus 0. All right. So this first term, because this location here is a point of stable equilibrium, my potential energy is a minimum. I can go ahead and call that constant value 0, and that's what I'll do. Boom, 0. Also, when you're at a point of stable equilibrium, notice that the derivative of u with respect to x at that location is 0, because it was an equilibrium point. That'll be true for all of them. All right. And my second derivative, because it is a stable equilibrium point, my slope is going from something negative to something positive. So this will just be a positive number, that u double prime. So that allows me to write my potential energy when I am close to x naught, or close to x equals 0 as I've defined it, as being 1/2 times some positive number times x squared, and let's just call that positive number k. So that's where our expression, that's why this potential energy here not only holds for Hooke's law, but it holds more generally for any time you're close to a stable equilibrium point. And now I really am out of time, but we're going to solve this system with 4 different general solutions next time, one of which you'll recognize from 240-250, but the other 3 are going to be kind of fresh and fun. See you Friday.
Okay. You got it on methods? You got it on methods?
Yeah.